On the 4th of October 1957, the then Union of Soviet Socialist Republic launched into space the first artificial satellite around the Earth. This was called Sputnik 1. This was little more than a radio beacon, but it indicated that the Soviet Union had the potential to launch into space large objects and, in principle, could launch nuclear weapons that could be directed at other nations. This caused quite a stir in the world at that time. Little more than a month later, on November 7th, 1957, the Sputnik 2 was launched. This was a much larger, much more substantial spacecraft. Most famously, it had the dog Laika on board, but it also had instrumentation from a number of distinguished researchers in the Soviet Union. One of the sets of instrumentation was a nuclear detection instrumentation from Sergei Vernov at Moscow State University. This was fully capable of measuring space radiation. The apogee of the spacecraft was not over the Soviet Union, was over Australia. The Soviets, the data were recorded, they were encoded and recorded by the Australians. The Soviets demanded the data, the Australians refused. The Australians demanded the code to interpret the data, the Soviets refused. And so the Vernov belts faded into oblivion, and it fell to these three guys to make the first great discovery of the space age. This is Wernher von Braun, who developed the Jupiter C or Juno rocket that launched Explorer 1, the model being held aloft here, into space. This is William Pickering, who was the head of the Jet Propulsion Laboratory at Caltech at that time. And in the middle, as Professor James Van Allen. Van Allen and his small group, students mostly, developed the instrumentation, and this really rocked the world. And the discoveries that the Earth is enshrouded in high-energy radiation belts led to Van Allen appearing on the cover of Time magazine not once but twice. What did they discover? Well, as I say, they discovered that the Earth is enveloped by toroids or belts of radiation. The inner belt, there are sort of two, or there were thought to be two sort of concentric belts. The inner one, which was the first of the particle distributions that were really measured in space probably, were made up of very high energy protons caused by interaction of cosmic rays with the Earth's upper atmosphere. And then an outer belt of very high energy electrons. It's much more variable. Interestingly, almost as soon as the belts were discovered, there began to be a more sinister and classified component to space radiation exploration. And this was led by Nicholas Christopoulos, who was at the Livermore Laboratory at that time. And unbeknownst to Van Allen co-workers, Christopoulos had been proposing to Livermore management that powerful nuclear weapons should be exploded in space, that there ought to be entrainment of those high-energy fission electrons from the nuclear explosions, and that those would constitute such a barrier to Russian satellites and Russian missiles directed at the United States that it would constitute a defensive shield. Van Allen and co-workers were read into the program, as they say in classified circles, pretty quickly, and over the space of 2.5 months developed a new satellite, Explorer 4, with all the instrumentation, and were ready to go when the first of the classified shots, they were known as the Argus shots, were in fact exploded in space. They were relatively small weapons, about 10 kilotons or so, and they deposited fission electrons and certainly proved the Christopoulos effect. However, that wasn't good enough for the people who were doing this kind of thing, and so in 1962 they exploded a much, much larger nuclear weapon called Starfish. This was well over a megaton in energy, and it was exploded over Johnson Island, the South Pacific, and it put into space in a huge flux of high-energy particles. These, I don't know if you can see it from the back, but each of these contours is like a third of an order of magnitude. So there were probably at least several million times more electrons put into the near-Earth environment than had probably existed before. Of course, Van Allen and coworkers had barely scratched the surface. The ink was hardly dry on the papers of discovery before the humans messed up the space environment as they had been doing other things, and really caused the radiation environment to be greatly altered. Because of these very high energy particles, at least a dozen or so spacecraft, and at least 5 or 6 that we have well documented, were actually destroyed by the radiation and ceased to operate because of this intense radiation. We'll come back to this story a little bit later, but hand in hand with the scientific exploration of the radiation belts, there has always been sort of a space weather or a concern about their impact on human technology. So over the years since the late 1950s, we've learned a great deal about the Earth's space environment. You may have seen from time to time the kind of cartoons in textbooks or magazine articles. And they paint a nice laminar picture, like everything is pretty static and behaved. In fact, the space environment around us is changing on essentially all time scales, from less than a second to millennia and beyond. The Earth magnetic field emanating from the molten core constitutes an umbrella, the magnetosphere that shields us from the onflowing solar wind and the charged particles that come from the sun. This boundary is called the Magnetopause. It undulates and has a great deal of structure. The region closer to the Earth is populated by cold plasma. It's called a plasmasphere, charged gas of material. Also quite high energy ions that constitute the extraterrestrial ring current, and then the Van Allen belts. And these are all commingled together. And these can be dramatically altered by changing flow of particles and gas from the sun. And a lot of that energy can enter the system and be stored in a vast reservoir on the night side, a comet-like tail called the plasma sheet. And then one of the most interesting things occurs when the interplanetary magnetic field embedded in the solar wind has the right orientation. It can interconnect with the magnetic field of the Earth and thereby open the gate and allow energy to flow deeply into the Earth's magnetosphere. When it does so, this can enhance particle acceleration. This can flow down into the polar regions and can also dissipate energy by enhancing the ring current, the Van Allen belts, and that's some of the things that we've been studying in this cosmic laboratory in our backyard. Those auroral particles, of course, give us some of the most fascinating of natural displays, being able to see aurora from above, but maybe even more spectacularly, seeing them from below. And anyone who's seen the aurora despairs of ever being able to explain in detail how those work. But I'm going to talk to you about the radiation belt storm probes, which were later renamed the Van Allen probes, and also touch a little bit on another mission called the Magnetosphere Multiscale Mission, MMS. Now, the sun is clearly the driver of most of the environmental change. Many of the radiation belt changes that we see really come about because of the sun. This is an artist's concept, a NASA concept of what we call coronal mass ejection. This is a large blast of material due to instabilities on the sun. These blasts can move out at perhaps 6 or 7 million miles an hour. They can have a mass of 10 billion tons of material or so. As I was illustrating before, they can interact with the Earth's magnetosphere, opening the gate, imparting huge amounts of energy, very large amounts of energy into the system, and ultimately enhancing the aurora and enhancing the radiation belts and everything else inside the magnetospheric system. We've been fortunate to see cases with modern instrumentation. For example, in late October of 2003, there was a spectacular active region on the sun. First, we saw a flare. The snow that you see in the picture is high-energy solar energetic particles. And then these are coronagraph pictures taken from upstream of the Earth. And the sequence again, so there's a flare. The white streaks are the charged particles interacting with the CCD camera. And then the sun would be here. And we, looking toward the sun, see this blast of material coming toward the Earth. And this was a very powerful enhancement of the Earth environment due to this coronal mass ejection, and it caused a wide variety of different kinds of effects. One of the spacecraft that we're very fortunate to have available to us in those days was called the Solar Anomalous and Magnetospheric Particle Explorer, SAMPEX. And I hope you like the kind of display I'm going to show you here, because I'm going to show you a lot of these kinds of pictures. And so if you don't like it, we'll talk about that. But anyway, this is an attempt to draw a three-dimensional picture of the radiation, especially the outer radiation belt. This is more of a two-dimensional cut, and the idea is that the SAMPEX spacecraft was in a low Earth orbit, high inclination orbit, and it flew through and cut through the different magnetic field lines. So these white things are magnetic field lines. The ones at high latitudes extend out indefinitely into space, but the ones near to Earth are sort of in a magnetic dipole, the kind of thing that you probably did in school, where you sprinkled iron filings onto a piece of paper above a magnet, and that traces out the magnetic field lines. And so SAMPEX was able to cut through the different field lines, and in effect was able to monitor what was going on each of these dipole field lines. And so we are going back to the earliest Van Allen and McElwain work. Actually, they came up with a system called the L shells, and it just was a measure of where the magnetic field lines crossed the equatorial plane measured in Earth radii. So one Earth radius would be near the Earth's surface. 4 Earth radii, for example, is where the GPS, the global positioning satellites, tend to operate. The distance of 6.5 Earth radii is out where the communication satellites like to live, staying at one fixed point above the Earth. At any rate, SAMPEX was launched in 1992, and it operated successfully for over 20 years. And it made measurements, and here if you looked at this now, and just think of this as radial distance out from the Earth, then you can see the inner Van Allen belt, probably the region where there are strong enhancements of high-energy protons from time to time. There's this slot region, empty region between the belts, and then the outer Van Allen belt, which varies very strongly. My colleague Chen-Lin Lee here produced these kinds of figures and put on the solar wind speed, the sunspot number, just a lot of information here. You could look at this for the rest of the hour, just looking at all the different kinds of things. But what you really see is that the outer Van Allen belt can be highly variable, can change almost on a knife edge from being weak and anemic to being very powerful. One of the most interesting things we actually saw with SAMPEX was associated with the animation I just showed you of the sun, that in October 2003, the radiation belts were, first of all, essentially wiped out and then reformed in a completely different location. In the place where you expected no particles, where there's usually a paucity of particles, the Van Allen belts reformed in this slot region and filled the inner zone with high-energy electrons for quite an extended period of time. Again, we'll come back to that. So anyway, the point was from the SAMPEX work was that what we thought we understood so well back in Van Allen's day, that there were many, many questions about why are the radiation belts changing so rapidly, how are particles lost, how are they re-accelerated, and really what's going on. In this Halloween storm, the end of October, it was known as the Halloween storm. And we really saw that the belts were completely changed in configuration, that we saw the entire space environment. I won't go through the details of this exactly, just to tell you that it was quite striking that such a powerful event could have such dramatic impacts. So again, Lee et al. Have produced this recent figure that shows the kind of figure I was showing you before, but extended it even further. There were further exciting things in store for us. For example, the sun in 2008, 2009 became as quiet as it has been in the last 200 years or so. It went through an extraordinary, deep and long-lasting solar minimum. During that time, again, red here, this is a logarithmic scale, so this is several orders of magnitude variability, very intense back in the 90s, quieter during the previous sunspot maximum, but during this minimum, the radiation belts virtually disappeared for a couple of years. It was really immensely quiet, and then came back to life. So given all of this amazing kind of hints of how dynamic the radiation belts were and are, it was realized that despite this being a 50-year-old topic, that there were lots of things to understand and learn better. And after all, this is a laboratory that we do have in our neighborhood where we can study processes of great cosmic significance. How are particles accelerated, transported, and lost is one of the key goals of astrophysics more broadly. So NASA put together what it called Science Definition Team. The goal was to define a new mission that would address the topic of how acceleration and loss occur, understand the creation and loss of these new radiation belts, understanding more deep kind of issues related to what it takes for such acceleration to occur, whether you have to have seed or source populations, and develop new predictive kind of models, and all that is underway. And so the key was to understand the outer belt, to understand this region where there aren't so many particles usually, and then to understand the inner belt more. There were really a lot of things that were required then to have detection systems that could address very high intensities, low intensities, be able to measure electrons in the presence of high energy protons, and so forth. And so we were tasked, when we were selected in this competition, to build an instrument at the University of Colorado called the Relativistic Electron-Proton Telescope. And the goal of this was to build an instrument that could cope with this. And here you see what we often do in physics is try to look at the energy spectrum, the distribution, the intensity versus energy for particle distributions. We realized from the models that we're going to have to deal with very low intensities in certain parts of the system, in the slot region, for example, and also deal with perhaps 6 or 7 orders of magnitude higher intensity in different places. So this really required a lot of nuclear physics and a lot of careful design in order to adapt to this huge dynamic range, to be able to have the sensitivity to measure things that were interesting near the low intensity end of the system, but also to have the ability to look at the, let's see, we're a little saturated here. Let me just do this, okay. And then to be able to deal with very high intensities and thereby be able to minimize dead time, to reduce the pileup possibility of lower energy particles masquerading as high energy particles, to reduce chance coincidences throughout the range, and to also deal with the fact that as you're being bombarded by these very high energy electrons, they tend to produce X-rays that can get in and spoof your detector system. So we built an instrument payload that was able to do all that. We heard in today's talks at the meeting about using GEANT to model the interaction of particles with the atmosphere. Well, it can also be used to model the interaction, and it was originally designed to measure the interaction with particle detection systems, but we decided to build this with a silicon detector stack, to have heroic shielding around this, both tungsten and aluminum, to minimize the side penetration, to have a very sophisticated collimator, and to test the interaction by bombarding this in the computer sense, and to be able to show that we were going to be able to collect all the energy that came in from the incident particles coming through the collimator. And this led to, this is sort of a schematic diagram of our baby, the Relativistic Electron-Proton Telescope, REPT. And this was like a doorstop. It's pretty massive and really was designed to be able to operate in this very hostile environment. So on the 30th of August of 2012, just about 4 years ago, in a beautiful early morning launch from Cape Canaveral in Florida, an Atlas V rocket blasted into space carrying 2 identical spacecraft that had these and many other instruments on board. The radiation belt storm probes were launched into precisely their expected orbit, and they were fully deployed, again, right on schedule. And after some initial deployment of communication antennas and a couple of the magnetometer things, then subsequently the long 100-meter tip-to-tip antennas were deployed and so on. The idea was for these spacecraft to fly through the entire radiation belt region, to have the two spacecraft first close together, but then in slightly different orbits so that they would separate over spatial distances over time, and to be able then to sample and to measure right where we think the acceleration was going on. And so these two spacecraft, as I say, were both successfully deployed. And it was really a pleasure to see that, that things were moving along. It was an incredibly sophisticated payload with full measurement of the electric fields, the magnetic fields, the wave fields, and a full range of charged particles from the lowest energies up to the very highest energies, including from the National Reconnaissance Office, an instrument that was able to measure up to GeV kind of energies to understand the inner radiation belt better. And as I say, in addition to the in situ measurements here, having these very long antennas allows to sample broadly the wave fields around. The idea was for these two probes to fly close together but at slightly different periods, and thereby they would separate in space, and one would lap the other, and they would actually then be able to also migrate around the Earth so that we were sort of sampling all parts of the magnetospheric system. Now, I mentioned to you that SAMPEX was launched in 1992. We considered ourselves lucky if we made it through the 2000 sunspot maximum. This is a plot of altitude versus time. Many of you may be familiar with the fact that atmospheric drag is a phenomenon. As the atmosphere heats up, it can interact with spacecraft and cause them to slow down and essentially be taken out of orbit by this drag phenomenon. We made it through the 2000 sunspot peak, but we also knew that with the sunspot activity rising in 2010 and beyond, that SAMPEX was going to re-enter the atmosphere. And so we really were anxious to turn on the radiation belt storm probes instruments as quickly as possible. So we went on a campaign. Instead of turning on our REPT instrument as planned, like 6 weeks after the launch, just as the normal sequence of commissioning, we insisted that it be turned on 2.5 days after launch, and we were very fortunate that it did. In fact, SAMPEX, may it rest in peace, entered, and in pieces perhaps, it re-entered the atmosphere in November of 2012, just a few days after the Van Allen probes were renamed as Van Allen probes, actually. But anyway, we turned on just a couple of days after the launch of the radiation belt storm probes, and we were quite fortunate to be right in the middle of an intense event. So here's our L versus time plots, as we call them again, the distance versus time. And it's the same deal here with multiple orders of magnitude represented by the color. And when we launched, we were right in the middle of a very intense enhancement of the outer radiation belts, and everything was neat. We saw the inner zone, we saw the slot region, we saw the outer zone strongly enhanced. But then, just a short while later, a lot of the outer belt was eroded away. This black really means that a lot of those particles were quickly lost. And then we saw something, this persistent feature, day after day, where this belt of particles was there. Our first thought was that there must be something wrong with the instrumentation, but my engineers assured me that couldn't possibly be true. And so we really began to look at physical kind of effects for this, but it appeared that there were not two belts, as Van Allen had said, but really three belts. There was the outer belt, this what we dubbed the storage ring, and then the inner zone. I'm going to show you an animation now that just tries to show this. And so instead of just showing the data in a kind of a simple two-dimensional picture, I'm going to lay down orbit after orbit on this kind of cut in a magnetic meridian just to show you. So we're laying down 3 days at a time here, taking old orbits off and adding new orbits. Well, what you see as this line moves across is that this inner belt, inner outer belt, if you will, just stays there and stays there, even though the outer part is changing quite dramatically. And then along came an interplanetary disturbance, like a knife edge, the belt disappeared, and then just a week or two later, the outer belt was tremendously enhanced again. So putting this more into a graphic kind of picture, this was quite unexpected, I think, in most people's minds, but that there was the inner and outer belt indeed, but that there was this third Van Allen belt, and this was published in the journal Science and has led to a huge number of papers that have been examining the physics of why this kind of third belt is there and maybe why it wasn't so well appreciated before or was really unknown before. So in addition to having the measurement of the particles, the high energy particles, of course, the Van Allen probes also had plasma, had wave measurements, and this has really given us a tremendous new window on how particle acceleration occurs in the Van Allen belts and hence by extension to other planetary systems. We are also beneficiaries of having extensive measurements of the solar wind and what the sun is doing. So we have both the driver and the response in hand. The sun has been quieter, I suppose you could say, than usual, but nonetheless we have beautiful data from what's called the Solar Dynamics Observatory, taking spectacular pictures of the sun, seeing from the SOHO spacecraft these kind of coronal mass ejections, these halo events that are coming out toward the sun. And so just after the launch of Van Allen probes, the sun was once again quite active, and we had a pair of spacecraft called Stereo Ahead and Stereo Behind, Stereo A and B, and they were able to see many of the solar drivers. So again, this is the sun being blocked by an occulting disk, and here looking from the side is looking at a blast of material coming out, again, probably several million miles an hour, heading straight toward the Earth. And so the stereo spacecraft let us see that. We have models now that allow us to really model such propagation in sort of 2 and 3 dimensions. And this, at the center of that white dot is where the sun is located. The yellow dot there is the Earth. Other things that NASA cares about, that we care about, other spacecraft, other planets. But what this model shows is just taking the data I was showing you and just showing how this rapidly propagates out. And in this particular case, the Earth was right in the blast wave of this disturbance from the sun. And this is early October. And what this led to, here again is a picture. Now we've turned our Earth on its side, so you can sort of see what this radial distance translates to. And this is the form of the plots that you've known to grow and love here. But almost like a knife edge, the particles disappear, and then again, like a knife edge, they suddenly appear, and they are formed throughout much of the outer radiation region, and then slowly die away. And so the Van Allen mission has more than met its goals, I think, of being able to witness directly the loss and reformation of the belts. Why do we have 2 spacecraft? Well, it's really to help us separate the kind of space and time behavior. This is a blow-up of that knife edge that I was showing you before, just a couple of days in October. And here's laying down the orbits of the 2 spacecraft. You see them overlapping one another. And here's the little vestige of this storage ring. And you see that in this outer part, at the higher L values, 4 or 5 Earth radii, there's really nothing, no measurable flux. And then all of a sudden, deep inside the outer belt region, you go from an orbit where there's nothing to suddenly there's a high intensity of particles. And so we can really watch quite in exquisite detail the sudden appearance of these high energy particles. In a paper by Jeff Reeves and coworkers, we were able to go through and study this, looking not just at the intensities of the particles, but what we call phase-space density, a way of separating out the kind of changes that might come about from just magnetic field variations or fluctuations. And this is another paper published in Science, where we saw the time here. This is the radial distance again. This is the density of these particles in space. But there were very low near background levels, and then these built up. But they built up not by coming from outside into the system, but they built up locally. This is a smoking gun for seeing the local enhancement, local acceleration. So this is what had been argued about for years and years, decades really, about the local acceleration versus external kind of forcing of the system. So this is a nice diagram that Thorne et al., we published this in Nature, but really made the point that we could see the accelerator operating in, as I said, exquisite detail here, where first we have low energy particles coming in from the tail region. You remember the plasma sheet that I talked to you about in the animation. These particles generate waves in what's called the chorus mode, but they can interact back with the particles. They can accelerate the particles rapidly, and I'll tell you a little bit more in a second about how quickly that acceleration can occur. But they build up in a localized region in radial distance here to high levels, and then they sort of spread out and fill up the entire outer zone. So you go from essentially an absence of Van Allen belts to a strong presence of the outer belt, and this can occur on amazingly rapid timescales. So again, the story, if you will, for the highest energy particles is one of acceleration, remnants, and then sudden loss. And this has really, I think, been a great unifying activity for our field to be able to bring together the low energy, high energy particles, the waves and fields. There was quite a fascinating period in March of 2013. We've become dependent on this every year. In March now we have some interesting event that occurs, usually on St. Patrick's Day. So we thank the Irish or whoever are making that happen. But on this particular March in 2013, there was a long period of gradual enhancement and inward motion of particles. So this is an entire month of data. Again, I won't dwell on this in great detail other than to say it's just sort of a textbook example of the source coming from outside into the inner part of the system. But then all of a sudden an interplanetary disturbance comes through, wipes out the particles, and then they reappear at all energies simultaneously. And my colleague John Foster led a great study about this particular event period. And I won't go into huge detail about all the data other than to show you that here we're making measurements of the wave energy. Here we're making measurements of the lower energy particles, in this case about 50,000 volt electrons, not MeV electrons, but down here we're seeing the MeV electrons. And a kind of event that many in the audience, I know from the meeting, have studied extensively, magnetospheric substorms, that we usually think of as producing enhancements of the aurora, but not necessarily extending up to real high energies. In this particular instance, a substorm occurred suddenly and almost instantly, certainly within minutes, the radiation belts that had been depleted were building back up to very high levels. And so once again, our eyes were opened that the accelerator operating just a few hundred miles above our head can be extremely efficient and effective. So this is a figure in sort of a companion paper to the Foster one. This is a Baker et al. Paper where we looked at this period of time. We went through and carefully examined the change in the overall density of these particles, and the high-speed solar wind stream that initiated the slower process caused the buildup of particles over a period of a couple weeks. The coronal mass ejection built up the particles very quickly. So the thumbprint, the fingerprint of what happens for the slow process is that it can take multiple days or weeks to gradually build up by driving these particles out from the outer part of the system to the inner part, whereas the thumbprint for coronal mass ejection is that almost instantaneous kind of acceleration of particles. So this is now the 3-year kind of picture of data for 1.5 to 2 MeV electrons. Again, your favorite form of plot here, L versus time, but now this is a year by year. And you see, standing back and taking this broad view, that the whole picture is one of sort of punctuated equilibria, that you have some interplanetary disturbance from the sun that drives these enhancements, and then things gradually just go away. Sometimes you can have extended periods, as throughout the calendar year 2014, where very weak kind of interaction with the sun, and then more recent times we've had some very powerful storms again. So the radiation belts that textbooks might suggest are very slowly changing, often are anything but. Another thing was quite striking to us was that the particles seem to go into a certain distance. It's like they're being pushed into a certain distance but go no further. And that distance is about 2.8 Earth radii or so. And so we have taken a look at long runs of data, and you see here this goes into sort of a constant distance. Now, the old theories were that radial diffusion should be acting, and the particles should try to migrate their way in under just random scattering to move deeper and deeper in toward the Earth. Why not? But instead, there seemed to be a barrier that particles never penetrated further in than this distance. And if you plot the data in a different form, kind of like the spirographs that maybe you played with as a kid or so, and lay down these orbits, not in a local time, but in an actual geographic orbit. So the Van Allen probe B, laid down for a month's time, executes this complete walk around the Earth in this spirograph kind of pattern. And what you see is that the particles get in to a distance, but there are no particles in the inner part of the system at these higher energies. So another quite remarkable finding from the Van Allen probe's mission is that during this epoch, for the last several years, there have been essentially no highly relativistic, no highly greater than MeV kind of electrons, measurable fluxes of those in the inner part of the system. There are plenty of protons in here, and that is a fascinating story in its own right, but we had expected to see an inner belt and outer belt of the high energy guys, and when the data are analyzed fully, we find that there are no electrons in the inner part of the system. So this led to another Nature paper, the Impenetrable Barrier. It's like the particles were running into some kind of a wall in space. And this has remained quite an interesting puzzle. Again, working with John Foster and colleagues at MIT Haystack, and to the point of the symposium or the workshop that we're here to attend, we began to realize that there, and I actually observed very well with the Van Allen probes, that there are these intense VLF, very low frequency radio emissions that constitute a bubble, the so-called VLF, very low frequency wave bubble around the Earth. And that many of the discrete lines that you see here, this is frequency in kilohertz, and this is, I guess, radial distance in L coordinates. But you see that many of these discrete bands running across here, and these are actually transmitters that are communicating between the masters and the submarines at sea. And so this bubble of VLF energy is really quite remarkable. Out inside this bubble, the intensities of VLF waves can be easily 5 orders of magnitude higher than immediately outside. And the outer extent of this VLF bubble matches almost perfectly where the high energy electrons cease to penetrate more deeply. So the bubble is right inside this. Now this is up looking at 4 to 5 million electron volt electrons, very high energy guys. They're the ones that are almost perfectly excluded. So we were waiting for a really strong event, we were hoping for something like the Halloween storm of 2003 to really drive the system hard to see how well the high energy particles might penetrate in through this barrier, this apparent barrier. We had a beautiful coronal mass ejection seen from the earthward side on the 15th of March. Remember St. Patrick's Day? Well, this is St. Patrick's Day again. We had the REPT and other instruments on Van Allen probes operating very well. The coronal mass ejection hit the Earth, wiped out the particles, and they reformed. They reformed very powerfully. This goes up to 6 or 7 million electron volts. There was a very strong shock wave, very strong geomagnetic activity, everything that we might have hoped for. Again, I won't go into great detail here. Space plasma physicists love looking at wiggly lines and stuff, but I'll just content myself here with showing you some of the beautiful color data that we've represented the REPT data with. But we see fascinating angular distributions in space, probably caused by the compression of the magnetosphere and the loss of the particles. But both for the inbound A spacecraft and the outbound B spacecraft, the impenetrable barrier is still there, and it remained there throughout the strong driving for this event. So I don't know how well you can see this from the back, but what we were fascinated to do was to walk through the data orbit by orbit from the time when the radiation belts had virtually disappeared to the time that they were sort of fully developed. And what we found in this case, 2, 3, 4, 5 MeV was that the particles built up over the next days. Each one is color-coded a little, each orbit is color-coded a little bit differently. But what you see is the particles easily build up by 5 or 6 orders of magnitude and intensity outside this barrier distance, but they don't get any deeper than that, essentially. So they really go into the stopping point and move no further. So we can see, again, for those of you who are very quick at looking at the data, this is the high energy guys, this is lower energy, hundreds of kilovolt particles. This is plasma kind of energies, and once again, this is time, but radial distance is also portrayed on here. And the point is that the impenetrable barrier, even under this extreme forcing, having 1,000,000 times more particles right outside than inside, the particles still didn't get into the inner part of the system. The more medium energy particles easily penetrated through this barrier, and so we're really now struggling to understand what is it about the magnetosphere as a system that allows easy access for relatively low energy particles, but really doesn't allow the high energy particles to do anything. And so a picture that operates, we believe, under some conditions and maybe operates under many conditions is the one that's from John's most recent paper. And what it really says is this red region, which is the VLF bubble, really acts to scatter and to exclude the very high energy particles from following their kind of natural tendency to diffuse inward through this barrier region. And again, the picture here then is that outside the barrier, the wave fields, the wave intensities are relatively low. Inside, the wave intensities can be 100,000 times higher in intensity, and that meshes very well with where the inner edge of this outer zone really is. So in many ways, humans have been modifying our environment not only by exploding nuclear weapons in space, but also by sending waves out from ground-based transmitters that are probably helping to sculpt the radiation belts, and at least to some extent, under some circumstances, are one of the dominant features. So last part, in concession to my good friend Shin-Lin here, I just want to mention that we were able to use not only these very, very expensive NASA spacecraft, the Van Allen probes spacecraft, to study these kind of phenomena, but on the other end of the spectrum, to be able to use very low cost, very small spacecraft to make key observations, and at LASP, the Laboratory for Atmospheric and Space Physics, and in the Aerospace Engineering Department at CU. Students were involved with designing and building CubeSat, and I'll show you in the next slide what that really is. The CubeSat that we're talking about here was launched in, I guess it's not really operating still, but anyway, it was launched in September, just a couple of weeks after the Van Allen probes were launched. And this little spacecraft, which is a 10 centimeter by 30 centimeter, had on board a modified version of the REPT instrument. So it was called the REPT Integrated Little Experiment, REPTile. And REPTile was flying in a low Earth orbit trajectory and was able to make measurements that actually played a key role and also showed that this barrier was there at L2.8 down at low altitudes as well. So this is the South Atlantic anomaly where there were high energy protons coming into the system, but it was really beautiful to be able to take a really small, inexpensive spacecraft and get that to play with these very large brothers and to really get them all to tell a consistent story. So to wrap up here and leave some time for questions, I'd just like to ask the not totally rhetorical question, but why do we think energetic electrons are so important? What is it that's so important about them? And whether one is looking at hot spots on the sun or looking at the radiation regions around other planets like Jupiter and seeing the synchrotron emission that comes from deep within the radiation belts of Jupiter, or whether one is looking at the Crab Nebula, looking at X-rays and radio emissions coming from stellar objects like this, or indeed looking on huge scales as the radio lobes around extragalactic jets. All of those are really visible to us because the energetic electrons are moving in strong magnetic fields and are causing emissions that allow us to see these systems. So once again, to beat the point further, we have the chance in Earth's vicinity to study many of the processes that are going on in these much more remote astrophysical objects and to understand them in the kind of detail that's really needed to develop a predictive science. And so using our cosmic backyard to study processes of great and universal significance is really important. I'll just conclude by saying that the Van Allen probes have now been operating for 4 years. They are operating in conjunction with many other spacecraft in near-Earth orbit, and they're operating with spacecraft that are also in highly elliptical orbits that extend out essentially to the distance of the Moon. We are also using them in conjunction with European and other international Japanese satellites, operational satellites such as the GOES spacecraft from NOAA, and also investigations that are in near-Earth orbit but looking at the Sun. So together, all of these constitute quite an armada that has allowed us to look at the magnetosphere with new eyes, to be able to see the system as a system. And when combined with the measurements that are made of the Sun now, we are able to make this Sun-Earth connection in an unprecedented way. So to conclude, I would just say that I believe that the results from the radiation belt storm probes, the Van Allen probes mission, have been rewriting the textbooks about radiation belt structure, acceleration, transport, and loss. As Mike was kind enough to point out, I began my career with the James Van Allen, and I'm sure he would be very pleased to see that more than 50 years on, that there are still things to be learned about the radiation environments that he first discovered so many years ago. These data reveal distinctive behavior, multi-belt structure, barriers to penetration, the fact that acceleration can occur on such remarkable range of timescales. The super and ultra-relativistic electrons, I think we're very pleased that we're making such beautiful measurements of these very high-energy guys that have been neglected for these many decades. And I believe the Van Allen probes then join with the other solar and Earth observing spacecraft and ground-based systems to really give us views that we simply haven't had before, and especially their relevance to space weather. And so I think a new window really has been opened on understanding acceleration, yes, but also gradients and wave interactions. And I'm particularly intrigued these days with the question of how man-made transmitter waves might be helping also to shape the radiation belts from their pristine state. So with that, thank you very much.
It's one small step for man, one giant leap for mankind.